We now get introduced to our first type of spectroscopy called infrared spectroscopy or IR spectroscopy. Now, in general, spectroscopy examines the electromagnetic radiation absorbed by a molecule. And for infrared spectroscopy, you can see that that absorption is occurring in the infrared region of the electromagnetic spectrum. And what we see is that molecules in general absorb energy through their bonds. So we're going to be talking about bond vibrations, both bond stretching and bond bending, but mainly the stretching of bonds. So what happens is a molecule can absorb infrared radiation by stretching its bonds. Now, one thing to be very clear about IR spectroscopy is that it is very qualitative. There is nothing quantitative about it. And sometimes this can be a little bit frustrating for students, especially science students, because they're used to everything being kind of quantitative. In general chemistry, right, we learn about how to quantify everything. Well, IR spectroscopy is not quantitative. What it does is it tells us of the existence or the absence of functional groups. Notice it cannot tell us the exact structure, so we cannot solve for a structure of a particular molecule. All we can tell from an IR spectrum is whether or not it has certain functional groups and maybe not have other functional groups. So let's look at an example. Here is an IR spectrum. This is of cyclohexanone, so it doesn't really matter what it is at this point. But I just want to show you what an IR spectrum looks like. Notice on the x-axis we have what's called wave number. Wave number is the inverse of wavelength. And the reason why we do this is because, if you recall from general chemistry, energy is inversely related to wavelength. So if we plot wave number, the inverse of wavelength, then we see a direct correlation between energy and wave number. The higher the wave number, the higher the energy of absorption. Generally speaking, what we're looking at is we're looking at a range from about 400 inverse centimeters, or 400 wave numbers, to 4,000 wave numbers. Now in this particular spectrum, it's going out to 4,600, but in general we're looking between 4,000 and 400 inverse centimeters. And for our purposes, most of the IR spectrum has a lot of peaks, and we can never really distinguish between those peaks. So we're going to narrow it down even further and focus mainly in between 4,000 and 1,400. So we're really confining ourselves to this small window of absorbances. Now, like I said before, what we're looking at is we're looking at absorbances that are distinguishable characteristics of certain functional groups. Here we have a spectrum of isopropyl alcohol, and you see this very large absorption at 3365. Now that absorption occurs because of the oxygen-hydrogen bond stretch. So whenever you have an alcohol present, that OH bond stretch is going to stretch, and it generally shows up between 3,200 and 3,400 inverse centimeters. So when I see a very broad stretch, I know I have an alcohol present in my molecule. Notice that's all I can really tell about that particular molecule, that it has an alcohol present, right? So oftentimes you'll be asked to maybe compare, say, okay, well, here's the structure, and here are a variety of compounds. Can you pick out which compound corresponds to that particular structure? And so what you're doing is you're simply identifying functional groups. That's what you're doing. So here's another example. We have this is butylamine, and butylamine, notice, also has a stretch, an absorption, in the same region as alcohol. So amines, in general, have an NH stretch. So instead of an OH, we have an NH stretch, 3200 to 3400 also. So same region. However, notice the difference in the shape. So alcohols are broad, um, and amines are not quite as pronounced. First of all, they're not quite as pronounced. Second of all, their shapes are a little bit different. Now it happens that primary amines, and this is a primary amine, right? A nitrogen that only has one R group and it has two hydrogens coming off of it. So because of those two hydrogens, we get two signals. If it was a secondary amine, then there would only be one hydrogen coming off of it, and therefore only one nitrogen-hydrogen bond stretch, so you only get one signal. If it's a tertiary amine, you get no signals at all because there are no nitrogen-hydrogen bonds, right? So it's important to understand that. We're looking at a nitrogen-hydrogen bond. Another example here is of propionic acid. So propionic acid has an OH group, but notice the OH group doesn't look the same as the OH group of an alcohol. We often will say that carboxylic acids have an absorption that looks like a hairy beard, right? Look at that hairy beard. You can kind of see its hairiness to it. And it's extended over a much longer wave number than that of typical alcohols. So one of the things, characteristics is this big, if you see kind of this ugly spectrum with this big hairy beard, you should be thinking carboxylic acids. Another highlight happens to actually be this right here, right? This particular signal at 1722, which corresponds to the carbonyl group, the C carbon-oxygen double bond, which I'll talk about in just a little bit, right? Now, here I have an alkene, and if I think about the types of bonds that I have in this particular structure, I have carbon-carbon bonds, and I have carbon-hydrogen bonds. Now, the carbons are different hybridizations. There's sp3 carbons and there are sp2 carbons. Well, it happens that sp3 carbon-hydrogen bond stretches at between 2850 and 2990, so just below 3,000 inverse centimeters. And so you see here, we have all these peaks that are in that particular region. Well, the peak, or the series of peaks below 3,000 correspond to sp3 carbon-hydrogen bonds. sp2 carbon-hydrogen bonds show up above 3,000. So this little peak here at 3084 corresponds to a carbon-hydrogen bond stretch that is sp2 hybridized. And so we can distinguish between sp3 carbon-hydrogen bonds and sp2 carbon-hydrogen bonds based on where they show up in this narrow region of 2850 to 3100, right? Anything below 3000 corresponds to an sp3 carbon-hydrogen bond stretch. Anything above 3000 corresponds to an sp2 carbon-hydrogen bond stretch. But there also is another type of carbon-hydrogen bond stretch, and that would be an sp carbon-hydrogen bond stretch. And here's an example of that where I have an alkyne present. There's a carbon-hydrogen bond. And notice I have an absorption at 3277. And so we see that sp carbon-hydrogen bond stretches a little further, a little higher in energy than that of an sp2. So the highest energy is sp, then sp2, and then sp3 hybridization. And so we can distinguish between them. Also notice in this particular structure we also have sp2 carbons. That benzene ring consists of sp2 carbons and there are hydrogens coming off of it, and so we see an absorption right above 3000 at 3044, and that corresponds to the sp2 carbon hydrogen bond stretches. So now we can distinguish between the different types of carbon-hydrogen bond stretches, sp, sp2, or sp3. Now, one of the cool features is that when we look at carbon triple bonds, so a carbon-carbon triple bond or a carbon-nitrogen triple bond, they have very distinct absorptions between 2000 and 2300. Nothing else absorbs in this region other than triple bonds. And so if you see a peak at, in the region between, essentially between 2700 and 1800, that peak represents a triple bond, carbon-carbon triple bond or a carbon-nitrogen triple bond. And so you see with this particular example of benzyl nitrile, that absorption at 2230 corresponds to the carbon-nitrogen triple bond. Notice again, it has sp2 carbon hydrogens that absorb at 3072 inverse centimeters. Now the last kind of functional group or groups that I want to talk to you about and kind of highlight are carbonyl compounds. Now notice there are a lot of different types of carbonyl compounds. There's ketones, there's aldehydes, there's esters and acid chlorides, anhydrides, amides, and all of these have the carbonyl. And the carbonyl has a stretch around 1700. And the thing about that stretch is that generally speaking it is sharp, it's intense, so it's very easily distinguishable. So here we have a carbonyl that absorbs at 1719. Now it happens that this is a ketone, and ketones generally have an absorption around 1720, right? So this is 1719. But oftentimes, there are slight fluctuations in the electronic environment such that that absorption can shift a little bit. So when we see an absorption around 1700, we say we have a carbonyl. Can we say it's a ketone or an ester or another functional group that has that carbonyl? Oftentimes no, but there are other distinguishing factors that we may look at that can distinguish between one type of molecule and another type of molecule. And to show how that absorption can change from that 1790, if you look at this particular structure, right, it's a ketone, but it is what we refer to as a conjugated ketone because there is a pi bond right next to it. And so if you think about the hybridization of the oxygen and then the carbon, obviously are sp2 hybridized. Well, the carbon to the right of that with the double bond is also sp2 hybridized. Both of those carbons are sp2 hybridized. And so the electronic environment is set up in such a way that we can actually draw resonance structures placing a negative charge on the oxygen. The result is that we have a carbon-oxygen single bond. And so the bond of that carbon-oxygen double bond ends up getting a little bit weaker. So in general, conjugation decreases absorption strength because you're weakening the bond. And therefore, it requires less energy to get it to stretch. So we go from 1719 down to 1695. Now I highlight this because I want to make sure that you understand again this very qualitative nature. If I have an absorption around 1700, I can say it's a carbonyl. Other than that, without kind of fine-tuning things, I leave it at that until I have more evidence to suggest a more precise functional group. Okay? Now, If you look in your textbook, there's a table 9.4, that shows common absorptions of various functional groups. I'm not going to go into great detail about this, but you can see from this that obviously carbon-hydrogen bonds of alkanes we talked about. There's also a carbon-carbon bond that we typically don't really look at because it's below that kind of 1400 threshold, generally speaking. There are alkenes. You can look at, if you know you have an alkene, you can actually get into the region between 1400 and 400 inverse centimeters that we call the fingerprint region, and you can actually figure out what kind of alkenes, what kind of substitution pattern that alkene has. There are alkyne absorptions, alcohols we talked about, amines we talked about, aromatic hydrogen, carbon-hydrogen bonds that we talked about as well. And of course, there are a variety of carbonyl compounds that we've discussed, and you see there are subtle variations in absorbances between aldehydes and ketones, and that of esters and carboxylic acids. But in general, they all fit into this range of around 1700. And so that's a good thing to know when we're trying to qualitatively recognize functional groups. And that wraps up our brief introduction of infrared spectroscopy.